Indeterminate forms are important when we evaluate limits. Sometimes we may look at a limit and it may seem as though it is zero, or it may seem as though it is infinity. But in reality, it could be an entirely different number. What do we mean by an indeterminate form? There are certain forms which are considered to be indeterminate. First, I'm going to go for an indeterminate form of quotients where we have one, or I could write it as general indeterminate form. So when evaluating a limit, if we have 0 over 0 or infinity over infinity, then we have a indeterminate form. So for example, I have limit x approaches infinity, f of x over g of x, and we know if we have a quotient, we take the limit of the numerator and we take the limit of the denominator, and if the limit, it doesn't have to be infinity, it could be some a, so I'm just going to say a. And if we know that the limit of the numerator approaches 0 and the denominator approaches 0, then we have 0 over 0. So that would become a standard indeterminate form. In a similar manner, if limit x approaches a, f of x is infinity, limit x approaches a, g of x is infinity, technically plus or minus. Then limit x approaches a, f of x over g of x is infinity over infinity. That is also an indeterminate form. We also have indeterminate form in product. Consider 0 over 0, which is an indeterminate form. I could write this as 0 times 1 over 0. And we know 1 over 0 is infinity. Now, in algebra, we often call it as undefined, but technically speaking, in mathematics, it is infinity. In advanced math, we usually refer to as infinity. So this form, 0 times infinity, is an indeterminate form. Likewise, if we consider infinity over infinity, which is the indeterminate form that I addressed earlier, I will have infinity times infinity. I could write infinity as 1 over 0 that isn't the way I want to go about it. Oh, I'm sorry. I meant to say infinity over infinity. I could write it as infinity over 1 over 0. Any number divided by 0 is infinity. So now if we flip and multiply, we would have infinity times 0 over 1, which is still an indeterminate form. So the 0 over 0, infinity over infinity that I wrote just comes back again in a different form as infinity times 0 or 0 times infinity. We also have indeterminate form in differences. So if we have two functions, limit x approaches a, f of x, that goes to infinity, limit x approaches b, a, g of x approaches infinity, then limit x approaches a, f of x minus g of x would simply be equal to infinity minus infinity. One may think that this would be 0, but in evaluating limits, though, this is an indeterminate form. So the answer is not 0. Keep in mind, we're not simply doing regular math here, rather we are evaluating limits. When we evaluate limits, and if we end up having infinity minus infinity, then it is an indeterminate form. This goes back to the concept of which function is going to overtake which function. So is f of x going to take the lead, or is g of x going to take the lead? There's a tug of war between the two, and we may not know what the eventual answer is going to be in limit, and that is why we call it an indeterminate form. Then we have indeterminate form in powers. So type 1 here is 0 raised to the power 0. We know any number raised to the power of 0 is 1. It doesn't apply when we do limits. When we do limits, 0 raised 0 would be 1. And even in algebra, if one wants to evaluate 0 over 0, we would get 1. Any number raised to the power of 0 is 1, but when we evaluate limits, this will be an indeterminate form. Type 2 is infinity raised 0. Same argument. When we do basic algebra, a large number raised to the power of 0 naturally is going to give us 1. But when we evaluate limits, though, we have to be careful. So infinity raised 0 is an indeterminate form. And last case, if limit x approaches a, f of x, and limit x approaches a, g of x, and let's say that approaches 1 and that approaches plus or minus infinity, then 1 raised infinity is an indeterminate form. Again, if you take the number 1 and suppose you raise it to the millionth power or the zillionth power, you would still get 1. In that case, we are simply evaluating a number. But when we are looking at limits, that is not the case. 1 raised infinity perhaps could be a number other than 1. This is a very unique feature that comes into play when we take limits. So oftentimes we evaluate limits with the use of logarithmic differentiation, implicit differentiation, or one of those to come up with an answer. But fundamentally, there is a rule that we use to evaluate the limits. And that goes back to what we call, that is what we call the L'Hopital's rule. So, L'Hopital's rule simply concludes this. Suppose we have the indeterminate form zero over zero or infinity over infinity. And, which would simply mean limit x approaches a, f of x is equal to 0, and limit x approaches a, g of x is the same, then limit x approaches a, f of x over g of x is simply 0 over 0. Now, that is an indeterminate form, and what the rule states is if we want to evaluate the limit, the moment we recognize that something is an indeterminate form, we take the limit of the numerator, but instead of using f of x, we take the derivative of f of x divided by the limit x approaches a, the derivative of the denominator function. And then we would have the answer. Same argument applies for the indeterminate form of the type infinity over infinity. So when we have indeterminate form in powers, we make use of logarithmic differentiation or logarithmic manipulation to get back to the standard form of L'Hopital's rule. The only thing that we have to be cautious about is g prime of x is not equal to 0 on any interval containing a. In other words, the denominator cannot be 0. That is a requirement we have for L'Hopital's rule. So the key here is if we encounter an indeterminate form when evaluating the limit, then we take the derivative of the numerator, apply the limit, divided by the derivative of the denominator, apply the limit, and we'll have the final answer. Sometimes after one step of L'Hopital's rule, you may get an indeterminate form again, which would simply mean you have to apply L'Hopital rule one more time. And sometimes an algebraic manipulation could save you from applying L'Hopital's rule successively and being hopeless and lost, because you would keep on getting indeterminate forms over and over, in which case it simply implies that you have forgotten something that is algebraic. So here is an example where we have to evaluate the limit as x approaches 3. X minus 3 divided by x squared minus 9. Let's just take the limit. So we have 3 minus 3 divided by 3 squared minus 9. 0 divided by 9 minus 9, which is also 0. 0 over 0, when taking limits, is an indeterminate form. So they're asking if there is a more elementary method to evaluate this limit, and if there is one, they want us to use that also. I'm going to demonstrate both. Just by looking at it, I can factor the denominator as x plus 3 and x minus 3. If I cancel x minus 3 out, I'll have 1 over x plus 3. Now if I apply the limit, I end up getting 1 over 6. So what we initially thought as 0 over 0, and you might have put the answer as 0, in reality it's not 0. Rather it is 1 over 6, and that is the correct answer. Now we could do the same using L'Hopital's rule. What does the rule state? The rule states that we take the derivative of the numerator, then the derivative of the denominator, and then apply the limit. What is the derivative of x minus 3? It's 1. Derivative of the denominator is 2x. Now, when we apply the limit, it doesn't affect the numerator, but there is an x in the denominator, so we have 2 times 3. I end up getting the same answer, 1 over 6. Now you can see how the L'Hopital's rule is effective in finding limits when we have indeterminate forms. This is a similar problem, and we would like to find the limit as we approach 1. First, let's see if it is an indeterminate form. So limit x approaches 1, x cubed minus 2x squared plus 1 divided by x cubed minus 1. When we apply the limit, we have 1 cubed minus 2 times 1 squared plus 1 divided by 1 cubed minus 1. 1 minus 2 plus 1 divided by 1 minus 1. 2 minus 2 divided by 1 minus 1. We have 0 over 0, and that is an indeterminate form. Is there an elementary method that we can use to evaluate this limit? Perhaps there is. Could we factor the numerator somehow? The denominator, I could write it as x minus 1 times x squared plus x plus 1. Let's see if that works out. Yes. So what I did is I just used algebra. There is a standard identity. If you have a cubed minus b cubed, we can write it as a minus b times a squared plus ab plus b squared. And if we have a cubed plus b cubed, we'll have a plus b times a cubed minus, a squared minus ab plus b squared. That is a standard rule that we use. So I'll just use that. Now, I would like to know if I could do something with the numerator. Perhaps I can. Well, let's see if let's ask that question. Since I see x minus 1 in the denominator, we'll see if x minus 1 is a factor of x cubed minus 2x squared plus 1, so we can cancel things out. So we can use long division or synthetic division. I'll just use long division because some of you may not know synthetic division, but in this problem synthetic division is easier. So I'm going to multiply by x squared. I get x cubed minus x squared, subtract the 2, I'll have minus x squared plus 1, and when I multiply by x, I would get x squared. I need to have a 0 term here. 0 and 1, because we are missing x, minus x plus 1. I guess I'll just put a minus here. So I'll have minus x squared plus x, and that's it. So when I subtract those two would go away, I'll have minus x plus 1. And when I multiply by minus 1, I have minus x plus 1. And when I subtract the 2, I get 0. So clearly, x minus 1 is a factor. So I could write the numerator as x minus 1 times x squared minus x minus 1 divided by x minus 1 times x squared plus x plus 1. Those two would go away. So the limit x approaches 1, x cubed minus 2x squared plus 1 divided by the original function x cubed minus 1 is equal to taking the limit of x squared minus x minus 1 divided by x squared plus x plus 1, which would give us 1 minus 1 minus 1 divided by 1 squared plus 1 1 squared minus 1 minus 1 divided by 1 squared plus 1 plus 1. These two would go away. We have minus 1 over 3. Now, let's use L'Hopital's rule and see if we get the same answer. What does the rule state? If we want to find the limit, we take the derivative of the numerator, which is 3x squared minus 6x divided by 3x squared. When we plug in the limit, we end up getting 3 times 1 squared minus 6 times 1 divided by 3 times 1 squared. We end up getting minus 3 over 3. We get minus 1. There has to be a mistake here. I recognized it. That should be a negative 4x. Of course, L'Hopital's rule is easier in this case. So 4 times 1, which would give us negative 1. So in this problem, the elementary method is finding the factors and cancelling out the factors. But to find the factors, we had to use long division, which is extra work, unless you know it right away. But you can see L'Hopital's rule gave the answer in about 3 steps. So here is a method, or here is a problem where they suggest whether to use an elementary method, but just by looking at it, there is no elementary method because the numerator is a polynomial and the denominator is trigonometric, so the only way is L'Hopital's rule. But before that, we've got to check if this is in fact an indeterminate form. Let's apply the limit. The numerator limit would be 0. The denominator, 1 minus cosine of 0. But we know cosine of 0 is 1, so we have 1 minus 1, which is 0 over 0, and that is an indeterminate form. So we could use L'Hopital's rule. We have to take the derivative of the numerator. Derivative of the denominator. Derivative of 1 is 0. Derivative of cosine x is negative sine x. So we have limit x approaches 0 to x divided by sine x. Now you look at that and you say, oh, let's go ahead and apply the limit. So 2 times 0 divided by sine 0, which is 0 over 0 again, and that is an indeterminate form still. So we take the previous step and apply L'Hopital's rule one more time. Derivative of the numerator is 2. Derivative of the denominator is cosine x. Apply the limit. We have 2 over cosine 0. Cosine 0 is 1, so 2 over 1. The answer is 2. So here we have a case where so first we've got to determine whether this is in fact an indeterminate form. So let's apply the limit. We have 1 plus cosine pi divided by 1 minus cosine pi. Cosine pi is negative 1, so we have 1 minus 1 divided by, we have 1 minus of minus 1, so we get 1 plus 1 divided by 1 plus 1, we get 2. So we don't have an indeterminate form, so L'Hopital's rule doesn't apply. because we do not have an indeterminate form. So here we have an 8th degree polynomial and a 5th degree polynomial. Let's not even worry about an elementary method. Perhaps long division could help us if we divide, but it's not necessary. Because long division here is going to take a lot of time. So let's not even worry about it, and let's see first if it's an indeterminate form. So we have 1 raised 8 minus 1 divided by 1 raised 5 minus 1. 1 minus 1 over 1 minus 1, 0 over 0. It is an indeterminate form. So we use L'Hopital's rule. So limit t approaches 1, t raised 8 divided by minus 1 divided by t raised 5 minus 1. Take the derivative of the numerator, 8t squared, bad math, 8t raised 7 divided by 5t raised 4, which would be limit t approaches 1, 8 over 5, t raised 7 times t raised negative 4. That would be limit t approaches 1, 8 over 5. T bases are identical, add the powers. T raised 3. Apply the limit. We have eight over 5 times 1 cubed, which would give us 8 over 5. Let's first identify if the limit that we are going to evaluate is in fact an indeterminate form. So e raised x minus 1 minus x over x squared. Apply the limit. E raised 0 minus 1 minus 0 divided by 0 squared. 1 minus 1 divided by 0 squared, which is 0 over 0. We in fact have an indeterminate form. There isn't an elementary method here because we have exponentials mixed with polynomials. So let's take the derivative of the numerator. Derivative of e raised x is e raised x. Derivative of negative 1 is 0. Derivative of minus x is minus 1. Divided by derivative of x squared, we get 2x. Let's apply the limit. We get e raised 0 minus 1 divided by 2 times 0, which is 1 minus 1 over 0, 0 over 0. We still have an indeterminate form. So what do? We apply L'Hopital's rule again. So the next step is limit x approaches 0, e raised x minus 1 over 2x. That's where we ended up with last time in the first step, the first time we applied L'Hopital's rule. So we take the derivative again. Derivative of e raised x is e raised x. Derivative of negative 1 is 0. Derivative of 2x is 2. Now apply the limits. We have e raised 0 divided by 2. So 1 over 2. This would imply limit x approaches 0, e raised x minus 1 minus x over x squared is simply 1/2. We want to find the limit of this function. The first step is to evaluate the limit. So limit x approaches 0 square root of 1 plus 2x minus square root of 1 plus 4x divided by x. When we apply the limit, we have square root of 1 plus 2 times 0 minus square root of 1 plus 4 times 0 divided by 0. We have square root of 1 minus the square root of 1 divided by 0, which is 1 minus 1 over 0, and that would be 0 over 0, and that is an indeterminate form. So we could do an elementary method in this problem. Let's do that first. Now this is using algebra. So we have radicals in the numerator. So we multiply and divide by its conjugate. Now this is what we call rationalizing the numerator. Once we rationalize the numerator, sorry, again bad math there, the denominator should be square root of 1 plus 2x plus square root of 1 plus 4x. If you FOIL and multiply the numerator, you will simply end up getting square root of 1 plus 2x squared minus square root of 1 plus 4x squared. I would let you FOIL it to verify this would hold true. So the root and the square will get cancelled. Same here. So we would be left with 1 plus 2x minus 1 plus 4x. That would give us 1 plus 2x minus 1 minus 4x. The ones would go away. 2x minus 4x is minus 2x. So we've rationalized the numerator. So let's go ahead and rewrite our limit. So we have square root of 1 plus 2x minus square root of 1 plus 4x divided by x. And that would equal to limit x approaches 0. The numerator, after rationalizing, becomes negative 2x. And we have x square root of 1 plus 2x plus square root of 1 plus 4x. The x's would go away, and we'll have minus 2 divided by, I'm applying the limit, square root of 1 plus 2 times 0 plus square root of 1 plus 4 times 0, have negative 2 divided by square root of 1 plus square root of 1. We have negative 2 over 1 plus 1, which is 2. Negative 2 over 2, we get negative 1. Let's say if we get the same when we use L'Hopital's rule. What we have is limit x approaches 0, square root of 1 plus 2x minus square root of 1 plus 4x divided by x. And we have already identified that that is an indeterminate form. So we simply take the derivative of the numerator and the derivative of the denominator. So before I do that, let me rewrite the radical in terms of an exponent. Now I'm going to take the derivative of the numerator. So that would be 1/2 times 1 plus 2x raised 1/2 minus 1 times the derivative of the inside, which is 2, minus 1/2 1 plus 4x 1/2 minus 1 multiplied by the derivative of the inside, which is 4. So I am using power rule and chain rule of differentiation. The derivative of the denominator is simply 1. I can get rid of the 2's. I can get rid of the 2 and the 4 and put 2 there. So limit x approaches 0, 1 plus 2x raised negative 1/2 minus 1 plus 2x raised negative 1/2 multiplied by 2. Move things to the denominator. So we have 1 over 1 plus 2x square root of 1/2 minus 2 over, I believe that was 4x, 1 plus 4x raised 1/2. We could rewrite it in terms of radicals if you can understand it better. So limit x approaches 0, 1 plus square root of 1 plus 2x minus 2 over square root of 1 plus 4x. So we can apply the limit now. We will have 1 over square root of 1 plus 2 times 0 minus 2 over square root of 1 plus 4 times 0, which would be 1 over square root of 1 minus 2 over square root of 1, because 2 times 0 is 0, 0 plus 1 is 1, 4 times 0 is 0, 0 plus 1 is 1. So we end up having 1 over 1 minus 2 over 1, which is 1 minus 2. We end up getting negative 1, which is the same answer that we had previously using the elementary method, where we used rationalizing the numerator, which is pretty much using algebra, to find the limit. Here we use calculus and we use L'Hopital's rule to get the limit. Here is an interesting problem that involves exponents with a different base other than e. So the base is 2. First, we have to know if this is an indeterminate form. So let's apply the limit. So 0 times 2 raised 0 divided by 2 raised 0 minus 1. So 2 raised 0 is 1. 1 minus 1. 0 times 0 is 0. 1 minus 1 is 0. So we have an indeterminate form. So we can use L'Hopital's rule, or we can try to see if there is an elementary approach to this. Probably not. So what we're going to do is use L'Hopital's rule. Limit x approaches 0, x 2 raised x, divided by 2 raised x minus 1. So numerator, we have to use product rule. U is x, v is 2 raised x, u prime is 1, and v prime, what is v prime? V prime is 2 raised x times ln of 2. We've done this before, and if you don't recall, the way we do it is y equals 2 raised x. Take ln on both sides. Ln of y would be equal to x times ln of 2. Derivative on both sides, 1 over y times y prime equals 1 times ln of 2. Multiply by y on both sides, we have y times ln of 2, but y is simply 2 raised x, so 2 raised x ln of 2. So that's just like a side note on how we got the derivative of 2 raised x. Now we could use product rule, u v prime, so x 2 raised x ln of 2 minus 2 raised x divided by 2 raised x ln of 2 minus derivative of 1 is 0. So numerator, we simply did u v prime, plus v u prime, so that is 1. So we have x 2 raised x ln of 2 plus 2 raised x divided by 2 raised x ln of 2. Limit x approaches 0. We have a common 2 raised x in the numerator. If I pull that out, I have x ln of 2 plus 1 divided by 2 raised x ln of 2. Those two would go away, and we would have x ln of 2 plus 1 over ln of 2. Apply the limit. We have 0 times ln of 2 plus 1 over ln of 2. So the limit is 1 over ln of 2. So here we have limit x approaches infinity, sine pi over x. So first we've got to determine if this is in fact an indeterminate form. And this is limit at infinity, not an infinite limit. So if you apply the limit, we have infinity sine pi over infinity. That would give us infinity times 0. And that we know is an indeterminate form. So how do we go about doing this? We could write this as limit What I did is a bit of algebra. I know that if I took the denominator and I did flip and multiply, I would end up getting the same, which is x times sine pi over x. So I just moved that sine pi over x to the denominator. Now, if you apply the limit, we have infinity divided by 1 over sine pi over infinity. And that would be infinity over 1 divided by sine of 0. We know sine of 0 is 0, so we have 1 over 0, which is infinity over infinity. Is still an indeterminate form. But what I did is I converted the indeterminate form, which was in product, to a regular indeterminate form so that I could use L'Hopital's rule. So, using L'Hopital's rule, limit x approaches infinity, x sine pi over x would equal to limit x approaches infinity, x over 1 over sine pi over x. But we know 1 over sine is simply cosecant. So we have cosecant pi over x. Now we can take the derivative of the numerator and the derivative of the denominator. The derivative of the numerator is 1, and the derivative of cosecant pi over x is simply negative cosecant pi over x times tangent pi over x. Do not forget to multiply by the derivative of pi over x, which is chain rule. Because we simply don't have x, we rather have pi over x. So the derivative of pi over x is pi times negative 1 over x squared. Because the derivative of 1 over x is negative 1 over x squared. So what we have here is limit x approaches infinity, 1 over negative cosecant pi over x, tangent pi over x, multiplied by pi times negative 1 over x squared. So we have a fraction in the denominator. If we flip and multiply, we'll get negative x squared. But I don't want to skip a step, so I'll just write it that way and move negative x squared to the numerator. So now we can take the limit. So we have limit x approaches infinity, which would give us negative infinity squared, divided by pi negative cosecant pi over infinity times tangent pi over infinity, which is negative infinity. Negative infinity squared is still negative infinity, divided by pi negative cosecant pi over infinity is 0, times tangent pi over infinity is simply tangent 0. So we have negative infinity divided by pi. Negative cosecant 0 is 1 over sine 0, so minus 1 over sine 0, and we know tangent 0 is simply 0. But sine 0 is infinity, so we have negative infinity over pi times negative infinity times 0. The negatives can go away. We have infinity divided by pi times 0 times infinity. You may say, well, the denominator is simply 0 because we have 0 multiplied by infinity, but we can't do that because the denominator is an indeterminate form. So what do? We apply L'Hopital's rule one more time. So we have to apply the L'Hopital's rule one more time, and we will start at this step over there. So now we have limit x approaches infinity, negative x squared divided by pi. We have a negative in the denominator, negative cosecant pi over x, tangent pi over x. And get rid of the negatives, and we will have limit x approaches infinity, x squared divided by cosecant pi over x, tangent pi over x. Now we take the derivative of the numerator, derivative of the denominator, again. So the derivative of the numerator is straightforward. Which is 2x. The derivative in the denominator requires product rule. So u is cosecant x, v is tangent pi over x. U squared is negative cosecant pi over x times tangent pi over x. Oh no, made a horrendous mistake. The derivative of cosecant x is cotangent pi over x. That might change everything. Could actually make the problem easier than I thought. So let's go back and change that. So negative cosecant pi over infinity would result in negative cosecant 0. That is cotangent. So cotangent 0. Cotangent x is cosine x over sine x, which should be cosine 0 over sine 0. 1 over 0, that would be infinity. So that would be infinity. That is also infinity, which would give us infinity. Well, it didn't change much. We still end up having an indeterminate form, so we have to do this again regardless. But I made one mistake. It should be cotangent . Okay, I'm glad I caught it. Sorry. Cotangent pi over x. U prime would be negative cosecant pi over x. Cotangent pi over x. Do not forget chain rule. We have negative pi over x squared. And v prime is simply negative cosecant squared pi over x, because the derivative of cotangent x is negative cosecant squared pi over x, multiplied by the derivative of pi over x is negative pi over x squared. So u v prime, so cosecant pi over x, multiplied by v prime, negative pi over x squared, times negative cosecant squared pi over x, plus v cotangent pi over x, u prime, negative cosecant pi over x. So limit x approaches infinity, to x. We have a cosecant pi over x in common. We have pi over x squared in common. So if we pull that out, we have cosecant squared pi over x plus cotangent pi over x. We can move the x squared to the numerator. So limit x approaches infinity, 2x cubed divided by cosecant pi over x multiplied by cosecant squared pi over x plus cotangent pi over x. Apply the limit. The numerator would be infinity. The denominator is 1 over 0, that is infinity. And we have infinity squared for cosecant squared pi over infinity is cosecant squared 0. Same here, pi over infinity, that should be 0. So we have infinity divided by infinity times cosecant squared 0 plus cotangent 0. Cotangent 0, again 0 over sine 0. That would be infinity. Cosecant 0 is 1 over sine squared 0. One over 0 is infinity, and 0 over 1 is 0. We have infinity over infinity times infinity, which gives us another indeterminate form, infinity over infinity. So looks like we have to apply L'Hopital's rule one more time. So now we have to take the derivative of the numerator and the derivative of the denominator. The derivative of the numerator is 6x squared divided by u is cosecant pi over x, v is cosecant squared pi over x plus cotangent pi over x. U prime is negative cosecant pi over x, cotangent pi over x. V prime, it's cosecant squared pi over x. Derivative of cotangent pi over x is negative cosecant squared pi over x. Derivative of cosecant pi over x, I could write it as cosecant pi over x times cosecant pi over x. Again, u, v, so cosecant pi over x, derivative of cosecant pi over x is negative cosecant pi over x, cotangent pi over x. Same, cosecant pi over x multiplied by negative cosecant pi over x, cotangent pi over x, which would give us negative 2 cosecant pi over x, cosecant pi over x, cotangent pi over x. Now you may say, could we have done it the easier way? Here I use product rule, but if you think about it, I could have used chain rule that would give me 2 times cosecant pi over x multiplied by the derivative of cosecant pi over x. We get cosecant pi over x cotangent pi over x with a negative. So the answer is the same. So you've got to pick and choose wisely. So cosecant squared pi over x cotangent pi over x. Now we can apply the limit. So u v prime is negative cosecant cubed forgot to multiply by pi over x squared with a negative. Same here, we've got to multiply by negative pi over x squared, negative pi over x squared. So u v prime would be the product of cosecant pi over x multiplied by negative 2 cosecant squared pi over x cotangent pi over x times negative pi over x squared plus vu prime cosecant squared pi over x plus cotangent pi over x multiplied by negative cosecant pi over x cotangent pi over x. So those are separate. And we have to multiply here by pi over x squared also with a negative. So I could write that term as positive and so now we have a pi over x squared in common, so I could move that out. And earlier we had a pi in the denominator before we applied the limit. So we have that pi already. So we'd have 1 over pi times pi over x squared, the negative. Move that to the numerator, you will have 6x raised 4 divided by pi. And what do we have? Cosecant pi over x multiplied by negative 2 cosecant squared pi over x cotangent pi over x plus cosecant cubed pi over x cotangent pi over x plus cosecant pi over x cotangent pi over x squared. So it seems like things keep on going. By looking at it, it seems like I'm going to get infinity over infinity again. So once you get this far, you got to stop and think, well, maybe there should be something else that we are missing. So what do? Let's say if we are missing something, because we keep applying L'Hopital's rule over and over again. So there has to be something else that we can do. So let's see if we can do something to get this right. So as I mentioned, it seems like things keep on going. Sometimes if this keeps happening, you just have to stop and ask yourself, could I have done something to this problem so that life is easier? So I went this far to just demonstrate how hard it could get if you keep on applying L'Hopital's rule. The question to ask here is, going back to the original problem, could you have done something so that this entire process could be avoided? So I'll put here, it's a caution as seen above. Could result in trouble, so you have to stop and check to see if something could be done algebraically. Okay, so what do I mean by that? Let's go back to the original problem itself. Limit x approaches infinity. We have x times sine pi over x. What I'm going to do here is I'm going to multiply and divide by pi. Which would mean limit x approaches infinity, pi times x over pi multiplied by sine pi over x. Look at these two. They seem to be the same. So I can do something there. So I'm going to pull pi out, and I can rewrite that expression as sine pi over x divided by pi over x. So you can apply the limit right here, but it could result in trouble again. So what I'm going to do is do another algebraic trick. Let u equals pi over x. This would mean as x approaches infinity, u must approach 0, because we have pi over infinity, which is 0. So I can rewrite the expression as sine u over u, which would mean pi. When you apply the limit, you have sine 0 over 0. And again, that is an indeterminate form. But you needn't lose hope. we can use L'Hopital's rule now. And we would get pi times limit u approaches 0 cosine u over 1. So that would be pi limit of cosine u over 1 would simply be cosine 0 over 1. Cosine 0 is 1, so the answer is pi times 1 over 1. We get pi. So the lesson to be learned from here is the L'Hopital's rule should make things simpler. If it's getting really, really hard as we move along, you can see as I applied L'Hopital's rule time and time again, the problem got more complex. Previously, in 2 steps, I got the answer when I had to recursively apply L'Hopital's rule. So if things are getting harder and harder as you move along, you have to stop and ask yourself, did you miss something? Did we miss something that could have avoided all this trouble? Perhaps there's an algebraic trick. And that's exactly what I did here, and it took me only a few steps to get to the limit of pi. So keep this cautionary tale in mind. So here is another example where we have limit x approaches infinity, x times ln of x minus 1 over x. And let's say if this is an indeterminate form to begin with. So we have infinity times ln of infinity minus 1 over infinity. Infinity times ln. 1 over infinity is 0. Infinity minus 0. Infinity ln of infinity. Ln of infinity is infinity. So we have infinity times infinity, which is simply infinity. So that infinity times infinity is not an indeterminate form. 0 times infinity is an indeterminate form. Infinity times infinity is not. So in this particular problem, since infinity times infinity is not an indeterminate form, L'Hopital's rule is not necessary. Okay, here we have another example. First, we've got to apply the limit to see if in fact we have an indeterminate form. So limit x approaches 0. Well, let's apply the limit. So we have 1 minus 2 times 0 raised 1 over 0. 1 minus 0 raised infinity. We have 1 raised infinity, and that is an indeterminate form. So specifically, this is an indeterminate form in powers. So what we should do, is we will simply say let y equals 1 minus 2x raised 1 over x. Since we have x in the exponent, and take ln on both sides. So ln of y would equal ln of 1 minus 2x raised 1 over x. 1 over x would come to the front, ln of 1 minus 2x. And let's take the limit on both sides. So limit x approaches infinity, ln of y is limit x approaches infinity, 1 over x, ln of 1 minus 2x. Or is it 0? It's 0, I'm sorry. So we will have limit x approaches 0, apply the limit, ln of 1 minus 2 times 0 divided by 0, which is ln of 1 over 0, ln of 1 divided by 0. So we get 0 over 0, which is an indeterminate form. But it is an indeterminate form where we can use L'Hopital's rule. So, using L'Hopital's rule, limit x approaches 0, ln of y equals limit x approaches 0. Ln of 1 minus 2x is 1 over 1 minus 2x multiplied by minus 2, chain rule, divided by derivative of x is simply 1. So we end up getting limit x approaches 0 minus 2 divided by 1 minus 2x. And that would give us, when we apply the limit, minus 2 divided by 1 minus 2 times 0, which is minus 2 over 1, we have minus 2. So, are we done? We are not. Keep in mind the limit we found is for ln of y, i.e. we did limit x approaches 0, ln of y, and that ended up to be getting one step ahead. So ln of y is negative 2. So we want to find the limit of y. So using limit properties, we can move the limit inside. So ln of limit x approaches 0 of y would be negative 2. Exponentiate on both sides. Erase ln of limit x approaches 0 of y would equal erase minus 2. Those two would go away. Limit x approaches 0 of y would be 1 over e squared. Limit x approaches 0, replace the y, which is 1 minus 2x raised 1 over x. And that is what we had in our problem. So the answer is 1 over e squared. So to summarize, if we have 0 over 0, infinity over infinity indeterminate forms, we directly use L'Hopital's rule. If we have infinity minus infinity or 0 times infinity, we manipulate algebraically to get 0 over 0 or infinity over infinity indeterminate forms. Then we apply L'Hopital's rule. And if we encounter the case of 0 raised infinity, infinity raised 0, or 1 raised infinity, then we use logarithms followed by substitution. We manipulate algebraically. Using properties of logarithms. Manipulate algebraically to get either 0 over 0 or infinity over infinity indeterminate forms. Then apply L'Hopital's rule, and you'd get the answer. But keep in mind, however, or once we get the limit, you exponentiate the result to get the limit of the original function. So these are the key things that we've got to remember when we try to evaluate limits with L'Hopital's rule. Specifically, I don't want you guys to forget this problem. This is a cautionary tale. I demonstrated it so that you guys can realize that repeated L'Hopital's rule could make things complicated. So whenever necessary, think of the problem and see if you can rewrite it in an algebraic way or rewrite it in a simpler way using algebraic manipulation, and then apply L'Hopital's rule so the problem is simplified and you can get to the answer right away.